Alright, we are continuing with homework fun. This is going to be section 13.3, concavity, and we're doing problem number 1. Alright, so in problems 1 through 6, a function and its second derivative are given. Determine the concavity of f and find x values where points of inflection occur. Alright, so we're given a function, f of x equals x to the fourth. Adjust the old camera there. Minus 3x cubed minus 6x squared plus 1. The second derivative is 6 times 2x plus 1 x minus 2. Alright, so we need to determine concavity and potential points of inflection. So we're going to use a sign chart similar to the one we've been using the last couple of chapters. Well, at least in section 13.1. But in this case, the sign chart is a little different because we're just examining potential candidates for inflection points. And in this case, if we set the second derivative equal to 0, our potential points of inflection are negative 1/2 and 1. So let's make up a sign chart. We have negative 1/2 and we have 1. We have the interval between negative 1/2 and 1. We have the interval from 1 to infinity, and the interval from negative infinity to negative 1/2. Okay. Let me adjust the lights. Okay, so... Alright, so now what we need to do is we need to examine the sign of the second derivative for each of these intervals, similar to what we did in section 1. So we have the portions of the derivative, which is 2x plus 1 and x minus 2. Sorry about my terrible lines. And then that'll tell us the sign of the second derivative, and then we'll be able to establish the concavity of the function. Okay, so let's look at a number less than negative 1/2. So let's look at negative 1. Plugging in negative 1 for 2x plus 1, we get negative 2 plus 1. That's negative. And plugging in negative 1 for x minus 2, we get negative 3, so that's negative. So that means the second derivative is positive. And that means we're going to have the function be concave up in that interval. Alright, let's look at the second interval between negative 1/2 and 1. So let's plug in 0. 0 here will give us a positive value. 0 here will give us a negative value. And so the second derivative will be negative. And because it's negative, the function will be concave down in that interval. And because that is the case, essentially what we have is the concavity is changing as the function crosses the value negative 1/2, and so this is going to be an inflection point. Negative 1/2 is an inflection point. Alright, let's look at the final interval between 1 and infinity. Let's plug in 2 for the first expression, we get a positive. Plugging in 2 for the second expression, Okay, so I screwed up here. Sorry. The second point is 2. You probably already caught that. Anyway, let's plug in 3. That's positive. That's positive. So we have a positive second derivative, and thus we're going to have a concave up behavior for the function in that final interval, and thus because concavity changes from concave down to concave up as the function goes through the value of 2, 2 will also be an inflection point. So we have inflection points at both -1/2 and 2, and we've demonstrated the nature of the concavity of the function in each of its intervals, and that pretty much does it for this problem.